A farmer is growing a field of wheat plants. The height, h centimeters, of each plant can be modeled by a normal distribution with mean mu and standard deviation sigma. We also know that the probability that the height of the plant of any given plant being less than 94.6 is 0.288. We also know that the probability of and the height of any given plant being 98.1 or greater than that is 0.434. Now it says a farmer measures 100 randomly selected plants. Any plant with a height greater than 98.1 centimeters is considered ready to harvest. Heights of plants are independent of one another. And we're asked two questions regarding this. The first one being, what is the probability that exactly 34 plants are ready to harvest? And the second question asks, what's the probability that exactly 34 plants are ready to harvest, given that fewer than 49 plants are ready to harvest? Another key piece of information we know is that in the last part, we were asked to find mu and sigma, and we found out that mu is about 97.3 and that sigma is 4.82. So that wasn't given in the question, but it is something that by this point we already have figured out in other ways. So first thing we need to do here is recognize that this is a binomial distribution, and therefore to find the probability that exactly 34 plants are ready to harvest, we need to use the binomial equation, okay? So that's first thing I'm going to write down is that this is a binomial, and it is a binomial specifically such that we have 100 as our n value, right? Now, why is 100 our n value? Because that's the number of plants that we're looking at here. And then our p-value, our probability of one success, is 0.434 because we're defining a success as any plant with a height greater than 98.1 centimeters. And the probability that any given plant is greater than that, according to the question, is 0.434. So that's the first thing we need to do. So now let's plug that into the probability equation for binomials, which is p probability that x is equal to exactly 34 is equal to n choose k times p to the power k times 1 minus p to the power k. And in this case, k is 34, right? K successes, 34 successes in n trials, 100 trials. So n choose k is 100 choose 34. And the reason we do this part is because the order doesn't actually matter. We just care about there being exactly 34. Doesn't necessarily have to be the first 34 that are successes and then the rest that are failures or any other given order. As long as exactly 34 are successes, regardless of the order, it doesn't actually make a difference to us. It would still count. Times probability of one success to the power of k, so power of 34. And then, over here, sorry, this should be n minus k, right? This should be the rest of them. And then we also, in order to have exactly 34, we need the rest of them to be failures, right? The rest of them must be failures. So we have to do find the probability of a failure, which is 1 minus the probability of a success. So 1 minus 0.434 is 0.566. And that's the power of n minus k. And n is 100, k is 34. So basically they're saying the other trials, the non-successes, there have to be the other 66 of them. Then if we multiply all of this out, we get 0.0133. And that might sound like a very low probability. I mean, it's barely over 1%, but this is also for exactly a very specific number of plants to be ready to harvest. And so it's not all that likely, to be honest. All right, then in part 2, we need to use our conditional probability. What is the probability that exactly 34 plants are ready to be harvested, given that fewer than 49 are ready to harvest? So what this should do is this should make the probability go up a little bit, because now we're not considering all the possibilities. We're only considering the possibilities where there are definitely fewer than 49 plants ready to harvest. So we need to use conditional probability. In order to do conditional probability, we're going to write it like this. Probability that x is equal to 34, given that x is less than 49, or we could even say less than or equal to 48, because this is a discrete distribution, it's not continuous. If this were continuous, we wouldn't be able to make that. But in this case, we can. We can say this is equal to the probability that x is exactly 34 over the probability that x is less than or equal to 48. So now the question is, how do we find out the probability of x being less than or equal to 48? Well, one way to do it is we could find the probability of 0, add the probability of 1, 2, 3, 4, all the way up to 48. However, that is going to take forever. So what we're going to do instead of that is we're going to find the z-score that matches this and use that to find the probability. So if we do that, we get that the probability of being less than or equal to 48 is going to be about 0.890474, and then probability of exactly 34 is up top, and that is going to equal to 0.0157 approximately. And there we go.